projection, but you write or construct it in a keyword projection. Oh, anybody? Do it here. Okay. Very good. Or make it beta D manose. Okay. Okay, second carbon, remember on the left. Okay, lang. The second carbon is, the OH is on the left. Yeah.
Up siya.
In the up. Not in the down.
Okay. Then the third carbon, the OH is still on the left. Fourth, the OH is on the right. Okay, very good. H, the H there. Yes. Fifth carbon. Yeah, H. Okay, you write it. Beta D manose. Very good. Okay, very good. It's easy. So in your quiz, in your exam, okay, more clarification. More. Alpha manose, alpha D manose. Okay, you're right. Or make it another. Say galactose. Bet alpha D galactose. So this one is galactose kani. Fisher, that's the Fisher projection. Always make your bond fall on the C. Because what is bonded together are the carbon atoms. Okay, class, huh? You have to keep track of the location of your bonds. The lines there that represents the bond. Carbon atoms are bonded together. Are you with me?
Yes.
Okay. Then for the OH, it's the oxygen that is bound with carbon, not the hydrogen. Okay? So the line there, say if you have the line and then you're asked to place the OH, then it should be the oxygen that is bonded to carbon, not the hydrogen. Are you with me? Second, third, fourth. Oh, fifth. Kulang pa gang. Kulang pa. First carbon, second, third, fourth. Naka fifth. Ang fifth is parinuganan. Kay D man siya. The OH is OH.
So both sides.
OH. D man siya. Then okay, that's D. You write there. Yes. D galactose. That is the Fisher projection. You convert it into Hayward projection. Alpha D galactose. Alpha D galactose. Here.
HO.
Alpha.
Tarong nga po dyan. Na-interchange na siya. Basta alpha or beta na. Depende. Pero dapat ang oxygen, mo bind diri that is OH. OH na. Diri na ang oxygen, mo bind dito. Sa anomeric carbon, in the Hayward projection, pwede siyang either alpha or beta. So if it's alpha, then down ang OH. If it's beta, then up. Okay? So what is that? That is alpha D
Galactose.
Okay, very good. That's alpha D galactose. Right? Hoy, dapat ang OH kung right. Ubos. Diba? Dapat ang OH sa right. So you have OH and the OH. If the OH location in the fissure is on the right, then it should be placed down. Only second carbon. Ang third. Okay, left. Up. Then kani, up hapon. Up
Alpha siya.
Sayop, they were the good. So why it's alpha? It's because the OH on the anomeric carbon is found on the right. It's down. Alpha C galactose. Okay, class. If it's beta D galactose, you just change the location of the OH. The OH should be up. H should be down. If it's beta D galactose. But if it's alpha, the OH is down. So if you are asked to construct the beta in Hayward projection, then the OH is up. The H is down. Get it? Yes. No, because we only make there is a fissure. There is a fissure. Fifth kani. Morning.
Gusto kaya po
Hindi na fifth kani. There na. So sa fissure projection mo na pinag-make carbon. Kung sa Hayward projection yung tanawon, anomeric carbon. Second, third, and fourth. Okay, again, ano nag-ibo? From fissure projection, it's easy, right? So we have this guy. Say for example, for the galactose is, okay, we all start with CHO, the first carbon. Second carbon, you start the OH on the right. So it's on the right, so here. And then left, then left, and then you have the penultimate carbon because they are all D. So the OH is always on the right. So you have the OH is on the right, and then you have the CH2OH. Okay, class. I notice you are not consensus with the placement of your your bond, no? As to what is bonded with. So what binds with carbon in hydroxide is the oxygen. What binds with carbon with another carbon? So you have to be, let the bond here. This one represents the bond. What is bonded with carbon here? The first carbon is on the second carbon. that is bounded. They're bounded together. Not the H. So, dapat careful mo sa inyong what falls on the bond. The line that represents the bond. Okay. Now, so this is how we describe the lactose. This is in the Fisher projection. In the Hayward projection, if you are converting it to Hayward projection, so you have here the O says 2OH, H ubos diha, and then you have to take note of the numeric carbon sa Hayward projection. Whether ang OH is on the down or up. Now, if you are asked for the alpha-D galactose, alpha down. Alpha representing Jesus, which he humbled himself, OH. Okay? So, OH is found on the down. And then, on the second carbon, kung naka sa right, ang OH is on the right, ubos din na siya. It's down. If you're on the right, you have to be humble. You have to be down. Okay? So, OH is on the right, so it has to be down on the Hayward projection. The third carbon is here. On the left. So, the OH is on top. Here, on the fourth carbon, OH is still on top. And then, of course, we have now the CH2OH up, then down is the H. Okay? CH2OH, then H. Yeah, pareho sila tanan ani. Oh, sa hexoses. Pareho sila tanan ani. And then we have here. So, opposite of the OH is of course the H. So it's easy. So, how to describe? You have the alpha D glucose. If it's beta D glucose, then you bring the OH up. Bring the OH up. And then here we have H. So that is beta. Okay? Any question? Any questions? No more? Okay, we still have topic. There we go. Okay, no more question with this? Okay, there are some other actually, no? No question with this beta and alpha. We have alpha down, beta up. So like this, from the Fisher projection to the Hayward projection. Okay, we also have these conformations. Para siya keyword sa chair conformation, para siya stretch na keyword, no, to become chair conformation. Chair conformation. Okay, now we have these physical properties of monosaccharides. Now, monosaccharides are colorless. You cannot see colors. No? Any color, it's colorless, without color. And they are crystalline solids. As you have noticed sa atoang table sugar, they are in a crystalline solids. And of course, they are very, very soluble in water. So when you place your table sugar in water, they will be dissolved. And they can also be dissolved in ethanol, but slightly soluble. Now we have some examples of sugars with, of course, sweetness relative to our table sugar, which is our kanina pang timpla o kape. So that is table sugar. That is sucrose. The sweetness of these sugars, they are quantified based on the sweetness of sucrose. Of course, we have the sucrose, our table sugar. We have 1. How about for our fructose, our table sugar, our fruit sugar, we have 1.74. So it's almost half as sweet as that of our table sugar. No? So, like for example, sa honey. Honey is almost, its sweetness is almost double with our table sugar. Okay? 1.74. So, or say 0.97, I should say, fruit sugar. But for our honey, it's not pure fructose. There are some other ingredients, no? But so it's less than, its sweetness is less than our table sugar. Ang fructose na to is in the fruits. Fruits. The sugars in our fruits. Now, glucose is very minimal, 0.74 compared to the sweetness of our table sugar. Maltose or malt sugar in beer making. That's why the beer, it contains sugar but it's not as sweet as that of our sucrose or honey. So it's 0.33. The lactose, 0.32, and then our milk is not as sweet as that of our table sugar. It's 0.16 lang. That's why there are some babies when they are fed through breastfeeding, and if the mama gets sick and the baby tasted the bottle feeding of it's synthetic milk, then sometimes they prefer the synthetic milk because it's sweeter than the mother's milk. Okay. 0.16. Okay. Now, we have artificial sweeteners. Of course, there's some others, class, but these are very, very common artificial sweeteners. And sometimes we are fooled by the labels. Say, sugar-free products. But what they're adding is any of this. Say for example, aspartame. Aspartame is very, very common in powdered juices, in iced tea. So, also nato siya sa Lady's Choice products. It contains aspartame. That's why it's lamig. But take note of its relative sweetness. Say for 1 tablespoon of table sugar, when you take that products with aspartame, you are taking in 180 tablespoons. Ana siya ka. Now, the same way ganang nasa mga milk tea, siya. It could be basig sa karin ng uban. No? Basta karin. Or acesulfame K, 200 times 200 times 450. That's why, especially with, say, your grandmothers or grandparents or your parents who are diabetic, take a look at those mga labels, ingredients of products. See, kasi may butang dito, sugar-free. Wala lagi table sugar, pero kami ang dibutang. Which is times Italian sweetness. So times 450 saccharin, acesulfame 200, aspartame 180. Ang very common aspartame. Very common. So if you plan to become slim, you avoid those products with this. Yeah. Times 2 po na. Times pila ni? Times 180 calories ang ma-intake nimo. Imagine mo nga, you're taking in 180 tablespoons of sugar. Table sugar. So you just imagine, so you its sweetness as to hundreds. 100 tons. Okay? Any question? So you have here. So the building blocks, the monosaccharides in carbohydrates are bonded together with glycosidic bond. So you have the bond from the anomeric carbon. Asan yung anomeric kani? The bond from the anomeric carbon. So to the OR group, to the OR group of another molecule. That's where the glycosidic bond is formed. Okay. Reduction. So reduction. Now when can we say that sugars can be classified as reducing or say non-reducing sugars? Now a carbohydrate that reacts with an oxidizing agent to form an algonic acid is classified as reducing sugar. Meaning, if there are some oxidizing agent here, okay, now like this, say, if there are some oxidizing agent, if this carbohydrate reacts with the oxidizing agent, then we can classify it as reducing sugar. But how? Without looking at the oxidizing agent yet, how can we say or describe a carbohydrate, whether it's reducing or non-reducing? Now, back to our hemiacetals. Now, when we say hemiacetal, you have CO, COH. Remember? If any aldoses, or say you have the aldehydes or aldose or ketones react with alcohol, that will form hemiacetal. You have CO, COH. Okay? Cocoa. Now, how to locate the hemiacetal group? Now, how can we know that sugars can be reducing or non-reducing? Now here, if the sugar whose end, okay. Now reducing sugars are sugars with hemiacetal found, which is said to be free at the end. So the sugar, the hemiacetal, is said to be free. And that hemiacetal group, that cocoa, will bind with the oxidizing agent. Now like this. Unsa ni siya? Like for example this. This is our glucose, say for example. Now, how to locate the hemiacetal? So you have carbon here, oxygen, carbon, then you have the oxygen and the OH. So you have cocoa. So this portion, COCOH, that is hemiacetal. And it's said to be free. Meaning it can react, that hemiacetal group can react with any oxidizing agent. So for sure, this sugar is reducing sugar. Because it has free hemiacetal group. Free, meaning it's not bound. So, meaning this hemiacetal can bind with any oxidizing agent. So, this is considered as reducing sugar. Okay? Now, how about the, say, okay, so you have there, hemiacetal group. Okay? Else? Okay, let's say. Now, how about for the for these disaccharides? Now, let's describe this different disaccharides as reducing or non-reducing sugars. Now, in the case of sucrose, sucrose is actually our table sugar. It is the most abundant disaccharide in the biological world. So it's the table sugar, pagpatimpla o kape, the one we're using in our kitchen. And it's obtained principally from the juice of sugar cane and sugar beets. So that's the origin of this sucrose. And it is said that sucrose is non-reducing. Why non-reducing? It does not contain any free hemiacetal at the end. Now, we have this structure of sucrose. So we have this glucose and we have this fructose. Because sucrose is made up of two sugar units bound with glycosidic bond. So you have the anomeric carbon here. So this is the glucose, this is the fructose. That constitutes our table sugar, our sucrose. Now, where you can find, would there be any hemiacetal free N? Okay, so for example, here, COCO, kay free man, kay kana, nakabound man siya, dali. So, dapat COCOC, kukok. So, acetal. Where is now the OH? So it's bound. It's not. So we cannot see any free hemiacetal group. So in other words, the sucrose is classified as non-reducing. So it may not react with the oxidizing agent. Okay? Now in your laboratory, you'll be performing an experiment that will help you identify whether the given different carbohydrates would be reducing or non-reducing. Okay? So you have here, for the sucrose, it's non-reducing because it doesn't have any free hemiacetal group. Okay? Okay, like this. Milk sugar, lactose. That's the principal sugar in the milk. Now, it consists of glucose and galactose. So, milk, say you have now the glucose and the galactose. So, you have the glucose and the galactose. Now, let's say, where is now the hemiacetal? Why lactose is considered as the reducing sugar? So, if this is our glucose, this is our galactose. Now, we have here, of course, this is our glycosidic bond in the anomeric carbon, no? Okay, and the fourth, 1,4, no? First carbon, fourth carbon, that's where the glycosidic bond occurs. Now, here, let's locate whether there is free hemiacetal or not. Okay, COCO, COCOH. So, it's said to be free. And this hemiacetal will react with the reducing or the oxidizing agent. That's why it's called reducing sugar. So, lactose is considered as reducing sugar because of its free hemiacetal group here. Ang coco, ang acetal group, you identify, look for the acetal group, COCOC. That is acetal group. COCOC. That is the acetal group. Are you with me? Hey, are you with me? Okay, so this is carbon, oxygen, carbon, oxygen, carbon. Coco. That is, say if you are asked to identify the acetal group, so it has here. But it does not, whether it's reducing or non-reducing, the acetal group is not based on. Now I say it is not used as basis to identify whether it's acetal or, reducing or non-reducing. So, what we're looking at here is the free hemiacetal group that will help identify the carbohydrates, whether it's reducing or non-reducing. So, like this, you have the COCOH. So, this portion is the hemiacetal group. Get it? Okay. made up of two glucose units. So it's the first glucose, the second glucose. So this is the glycosidic bond. Now we'll see whether it's reducing or non-reducing. Of course, it's reducing as mentioned. But let's see whether there is free hemiacetal group. So you have COCOH. So this is free hemiacetal. How about the acetal group? CO, C, COC. Wala na siya ikuan. Wala na siya acetal. Or here. Ano yan? COCOC. Naan. COCOC. That is acetal group. But we are not using this group to identify whether it's reducing or non-reducing. What we are looking at here is the free hemiacetal group. If you can find hemiacetal and it's not free, then that is not used as basis to identify whether a sugar is reducing or non-reducing. It should be free and found free at the end. So it can react with the oxidizing agent. Okay? So like this. So maltose or malt sugar is a reducing sugar. How about the polysaccharide? Now polysaccharide, you have the poly, several units of sugar, saccharide sugar. Say glucose, 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 glucose. So up to how many? Say up to 10,000 glucose units bonded together with glycosidic bond. That is how big is your polysaccharide. It's a big molecule. Okay? And joined together by glycosidic bonds. So we have some examples of polysaccharide starch. Now starch is a polymer of glucose. Taas kaya na siya, glucose, 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 straight. Like for example, ang upan, like we have some examples of types of starch. We have amylose or amylopectin. Amylose or amylopectin. Now for the amylose, it is said to be unbranched. Meaning straight lang na siya. Glucose, glucose, straight. Glucose, ilan na siya ka-thousands. Bonded together with glycosidic bond. Okay? So that is amylose. Now, say, you have here, and then you have, say for example, this is the last glucose in, say, in amylose. Now, the only free hemiacetal is only on the last glucose of amylose. And that is only where you could find the free hemiacetal. Now, that explains why in your laboratory, starch, which is amylose, may be considered as non-reducing. Though you can find a free hemiacetal at the end, but it's out of that big molecule, only one hemiacetal is free. Why? Because it's bound here. Only one hemiacetal is free, so it may not react well with oxidizing agents. So sometimes the color, you cannot see any change in color. And you may consider it as a non-reducing because it has only one free hemiacetal with that huge amount or huge size of molecule. But in the case of a starch or say a polysaccharide called amylopectin, amylopectin is branched. Na siya branch. So it's a branch and made up maybe of 10,000 glucose units joined by alpha-1,4 glycosidic bonds like this. This is first carbon. So you have here, see, this is now the example of amylopectin, branch siya. Glucose, glucose, glucose. Ano po glucose dili? Glucose diha, branch. So in other words, kaning glucose has free hemiacetal here. So pwede siya maka-bind with or attach with the oxidizing agent. Then another na po dito, So, in other words, when you are describing the amylopectin, which is also a polysaccharide, now, you may consider it as reducing sugars. Why? It will react with oxidizing agents because of several free hemiacetals that will react or interact with oxidizing agents. Okay? So that's the difference of the amylose, which is polysaccharide, and the amylopectin. This is unbranched, straight lang, linear, and this one is branched. Joined still by glycosidic branch. So branch siya. Okay? You have here, this is an example of amylopectin. Amylopectin, so na siya free diri. So this portion can be, this portion has to be free. Kana na po diha.